search feels broken when filters and counts disagree with ranked results. This builds faceted search in Postgres from Python with JSON-B filters, counts, and sane ranking. This is the pattern you'll be able to implement by the end, which ranks text, applies structured filters, and returns facet counts that align with the filtered results. I'm Professor Pi, teaching Search and IR with simple Python. Faceted search is what powers most product filters and category summaries. The problem I want you to feel is when you type a query, the top results look relevant, but the brand filters or color counts do not match those results. That gap breaks trust. Postgres gives us two nice tools to fix it. Full text search ranks text. JSON-B stores structured attributes. Together, they let us return ranked rows and coherent facet counts in the same query. At a high level, the idea is simple. We use Postgres full text search to score documents. We store attributes like brand and color as JSON-B, so filters are fast and expressive. When a user picks a filter, we run the same tsquery and the same JSON-B condition to both rank and count. The counts then reflect the filtered set, not the unfiltered universe. We will build a tiny, deterministic example that shows the whole flow. You will see a live connection from Python, a seeded items table with JSON-B attributes, a plain text search that ranks, a title boost, and a facet count that honors the text filter. That makes each step feel small before we combine them. Now we'll connect to the database. This example connects to a local PostgreSQL using psycopg and verifies the session. The psycopg.connect opens a client connection using the default Postgres database and localhost. Auto commit is enabled, so subsequent DDL and writes are applied immediately without an explicit commit. A cursor named cur is created to run SQL. The code executes a simple query that returns the current database and server version, then unpacks the first row into DB and ver. Finally, it prints the database name to confirm the connection is live. The printed database name confirms psycopg is talking to your local PostgreSQL instance. Next, we'll create a tiny dataset with JSON-B attributes. This code creates a minimal items table with title, body, and a JSON-B attrs field, then inserts two rows. The cur execute call issues multiple SQL statements in one round trip. It ensures the table exists, truncates any old data, and inserts two products. Each attrs value is built with JSON-B build object, so brand, color, and size are stored as queryable JSON-B keys. After loading, the code runs a count query to confirm how many rows are present and fetches the single result. The printed total shows a deterministic dataset is ready for the next steps. A small, clean seed makes later search results easy to interpret. Now, we'll run a simple full-text search and inspect ranks. This snippet performs a simple full-text search using PostgreSQL's tsrank. The variable q holds the user query text. The SQL builds a tsvector on the fly by concatenating title and body, and it turns the query into a tsquery via plain2 tsquery, which tokenizes and ands terms. The where clause filters to rows that match the tsquery, and order by sorts by tsrank descending, so higher relevance rows appear first, with a tie break on title. The cursor executes with q bound twice, once for ranking and once for filtering. The top results, title and score, are fetched. The printed rank shows the best match and its relevant strength. Next, we'll bias the rank toward title matches to prefer concise hits. This example boosts title matches using PostgreSQL's setWeight with tsrec. The query builds two tsvectors, one from title and one from body, then marks title as weight A and body as weight B before concatenating them. The tsRank function scores matches, giving more influence to A than B under the default weighting. So hits with query terms in the title climb. The where clause still uses a combined title plus body vector to ensure any relevant document can match. After execution, the code fetches the top score. Increasing the gap between weights emphasizes concise titles. Decreasing it makes body content contribute more. The printed boosted score reflects the title-first relevance policy. Finally, we'll show facet counts that respect the same text filter and a chosen JSON-B constraint. This code computes facet counts over JSON-B for the same base set as the text query. The variable Q holds the full text query, and cell carries a chosen filter. Here, brand equals alpha to constrain visible results. The SQL filters rows by the TS query match on title plus body, and applies the brand condition on the JSON-B column using the bracket X operator. It then groups by the extracted color field and returns counts sorted by frequency and name. The cursor executes with Q and the selected brand bound as parameters, and the first facet bucket is fetched. The printed color and count confirm that filters and search align to produce coherent facet tallies. To map this toy example into a real product, index your text with a materialized tsvector column, and build a GIN index on JSON-B keys. Use prepared statements from Python to keep latency low. On larger catalogs, you will want to test query plans and consider partial indexes for frequent filters. The pattern stays the same. Run the same TS query and JSON-B condition for both the result set and the facet aggregates. That alignment is what keeps counts honest. Recap. What it is: a practical Postgres pattern that regs text and computes facet counts from the same filtered set. When to use it: use it when you need consistent filters, fast rollups, and can host Postgres as your primary search layer. One caveat: full text ranking in Postgres is not a substitute for a tune vector or ANN index when semantic recall is required. Next step: tune the title versus body weight gap so ranking matches user expectations. Then measure how facet distributions shift. If short, practical IR helps, subscribe and watch the IR videos.